We will continue solving problems on chapter 3 today. So first, in problem 1, a tensile test uses a test specimen that has a gauge length of 50 millimeter and an area of 200 millimeter square. During the test, the specimen yields under a load of 98,000 Newton. The corresponding gauge length is equal to 50.23 millimeters. This is the 0.2% yield point. The maximum load of 168,000 Newton is reached at a gauge length of 64.2 millimeters. First, determine the yield strength. So, in order to determine the yield strength, all we have to do is to apply the formula. The yield strength is equal to what? It's equal to the force applied at yield, the force that will cause yield of the specimen, over A0. So F yield over A0. They gave us the value of the force that will lead to yield of the specimen, which is 98,000 Newton, and we divided by the initial area A0, which is 200 millimeters. Now, concerning unit, if the force is in Newton and the area is in millimeter square, then the yield strength you get will be in megapascal. And if you convert the area to meter square, then you will get a value in Pascal. Okay? Now, in part B, we want to calculate the modulus of elasticity. In order to calculate the modulus of elasticity, we need 2 points in the linear relation. So you know that in general, we have a curve, sigma function of epsilon. So of course, one of the points in general who will 0, 0. And we have the curve. Now, in order to determine the elasticity modulus, we have several possibilities. If we have any point before yield, if we know its characteristics, we can just say that if we consider the origin and this point, then we take delta sigma over delta epsilon, which is sigma at this point over epsilon at this point. But since here we don't have any information about any point before yield, we just know the yield point. And they said that the yield point was estimated based on the offset method, 0.2% offset method. What is this method? This method consider a point epsilon equal to 0.2%. So it will take epsilon equals to 0.002, which is very close to 0. And we draw a line that is parallel to the linear region. So it will intersect the curve with the yield point, okay? And of course, this is a very accurate method because epsilon 0.002 is very close to 0. And in this way, we can track the transition between elastic and plastic regions. So whenever they say the yield is determined based on this method, okay, then when you want to calculate E, you can say that E is the slope of this line, okay, is equal to delta sigma over delta epsilon, okay? Now, what is the 2 points of interest? The 2 points of interest are the one we started from, which correspond to epsilon 0.002, and for this point sigma is 0. And the second point is the one of intersection, is the yield point. And for this point, we know we already calculated the yield strength. And we can calculate epsilon if we know the corresponding gauge length. We know that the corresponding gauge length at the yield point is 50.23 millimeters. So all we have to do now to get epsilon at this point is to apply the formula that epsilon at yield is L final minus L0 over L0. So it's 50.23 minus 50 over 50. Then we get this number represents epsilon at yield point. So if I do the projection on epsilon axis, this will give me the value of epsilon at yield. Now, by going back to the formula, what is the slope of this line? The slope of this line is delta sigma of the 2 points. which is sigma yield minus sigma at the point of epsilon equals 0.002, which is 0, over delta epsilon, which is epsilon at yield, which is calculated. Okay, so it's epsilon yield minus epsilon of the start point, which is 0.002. Okay, so once I find epsilon at yield, I subtract from it 0.002, and then I divide sigma yield by this value. I get the elasticity modulus. And concerning the unit of elasticity modulus, it will be the same unit as the yield strength, because you know that epsilon has no unit. It's a ratio of lengths. So if you use yield strength in megapascal, you will get E in megapascal. If you use yield strength in gigapascal, you will have E in gigapascal. Any question on this?
Doctor, can you repeat how we got them? How we got the values? 50.23 or 50?
Yes. By definition, what is epsilon at yield? The value of the strain at yield point is equal to the length of the specimen at yield minus L0 over L0. Okay? Now, if you read the given, they said that at the yield point, what is the gauge length? It's 50.23. And what is the initial length of the specimen? It's 50 millimeters. So to calculate epsilon at yield point, you do 50.23 minus 50 over 50. Okay? And after you find this epsilon, you want to find delta epsilon. So you subtract from it what? You subtract from it. So here, if you want, this is delta epsilon. Okay? Delta epsilon is epsilon at yield, which is calculated from the following formula, minus epsilon at the initial point, which is 0.002.
Okay, I thought the 0.002 هي بالdenominator.
No, هلا هن no, it's minus. Okay, هيدي كلها minus هيدي. Okay?
Yes, thank you.
Okay. Now, part C calculates the tensile strength. The tensile strengths, as we know, correspond to the maximum stress, which is due to the maximum load. So the maximum load applied is given. The maximum load is 168,000 Newton. And to find the tensile strength, the formula is I do F max over A0. So here, all I have to do is to replace and just pay attention for units. If I use the force in Newton and the area in millimeters square, I will get the tensile strength in megapascal. Now, concerning the value of elongation, okay, to find the percent elongation. When they ask for the percent elongation, this means that I should calculate it at fracture point. Okay, so it's epsilon at fracture. So percent elongation is epsilon at fracture. Okay, so all I have to do now is to take the final length, which is at fracture, we have a length of 67.3 millimeter. So the percent elongation will be 67.3 minus L0 over L0. And I get the value, which is 34.6%. Pay attention. Here we will not use this value. And sometimes they give you values not needed. Okay, so this is to test your knowledge. So if they tell you when I will need to use 64.2, if they ask you what is the engineering strain at the maximum load, then you will use the corresponding length, which is 64.2. Okay, but when they ask for the percent elongation, I use the final length at fracture. Now, the other question, if the specimen neck to an area of 92 millimeters square, determine the percent reduction in area. So now to calculate the percent reduction in area, I apply the formula, which is A initial, A0, minus A final over A0, okay, over A0. So in this case, I will case the reduction in area. And you can see that the percentage of reduction in area is much higher than the elongation percentage, because the reduction in area will not take place over the whole specimen. It will only, at the end, in the necking part, you have a dramatical decrease in area just for the next part. Okay, this is why the percentage of area reduction will be higher than the percent of elongation. And these two index can be a characteristic of ductility. Okay, so ductility can be measured through percent elongation and through area reduction. And higher is the percent elongation and area reduction, higher is the ductility of the material. Okay.
Doctor?
Yes.
When we want to find the modulus, do we always subtract 0.002 from the epsilon?
If they tell you that this yield point is based on the offset method, yes. Okay.
Okay, they should mention it. Yeah.
Yes, they should mention this.
Okay.
If not, sometimes, when we use the offset method, when the yield point, which is the transition from elastic to plastic, is not very clear. In case the yield point on the figure is clear, then we don't need to do the offset method. So you simply say, you can use simply the formula sigma over epsilon. Over epsilon, you get E in this case. Okay. Or if you know any point on the elastic region between the yield and 0, 0, you can use this point, because this point, at the end, the elastic curve will start from 0, 0 until yield. Okay, so if you have any point in between, its characteristic sigma and epsilon. Okay, and the initial point is 0, 0. You can say simply that the slope is equal to sigma at this point over epsilon at this point. Okay, or even if you have any 2 points of below the yield, you can say it's delta sigma over delta epsilon. Okay.
Okay, thank you.
Any other question? So let us continue. Last time we have done the first step of this problem. We showed that the true strain is related to the engineering strain by the following formula. Now the second relation we will derive together is that sigma true is equal to sigma engineering times 1 plus epsilon. So in this case, first, whenever you want to demonstrate a relation, you should go back to the definition. What is sigma engineering? It's F over A0. What is sigma true? It's F over A. So here, to demonstrate this formula, I need to demonstrate that sigma true over sigma is equal to 1 plus epsilon. So let us find what is the ratio of sigma true over sigma. If I do sigma true over sigma, I divide these two equations. I get that the ratio of true stress over engineering stress is A0 over A. And A0 over A can be calculated from conservation of volume. From conservation of volume, and of course, please, before the necking, okay? This relation, we use it to transform from engineering to true values, but in reality, it's only valid before necking, okay? Why? Because from conservation of volume, since before necking, the elongation takes place over, the reduction of area takes place over the whole specimen, I can write that the volume at any instant is A times L and should be equal to the initial volume, which is A0 times L0. After necking, I cannot say that the volume is A times L because the reduction in area will only be for the next part, okay? But before necking, this relation apply, and I can say then that the ratio A0 over A is inversely proportional to the ratio of length, so it's L over L0. Then from the previous demonstration, we have seen together that L over L0 can be substituted by 1 plus engineering stress. Okay, so all I have to do now is to say that A0 over A is L over L0 is equal to 1 plus epsilon engineering. And then by replacing the ratio A0 over A in this formula, I will get that sigma true over sigma is equal to 1 plus epsilon engineering. And then when I take sigma to the other side, I can demonstrate my formula, which is that sigma true is equal to sigma engineering times 1 plus epsilon engineering. So in general, these two relations, you can use them to deduce the value of true and true strain and stress function of engineering stress and strain. Okay, so whenever you know the engineering strain, you use this formula to get the true strain, and whenever you know the engineering stress, you can use this formula to find the true stress. And of course, you can use them in the opposite way. So if you know the values of true strain and the true sigma, you can deduce then the value of engineering strain and engineering stress. Okay. So now, any question on this? Now we'll start problem 3. This is the most important problem because it involves a lot of parts. So first, in problem 3, the following force displacement data were collected during a tensile test in which the starting gauge length is equal to 100 millimeter and the cross-sectional area is equal to 150 millimeter square. So you have 6 points given, and for each point they gave us the displacement value, delta L. So displacement is delta L, which is L minus L0. And we have the force F, the corresponding force F applied on the specimen at each point. And from these characteristics, we will draw the engineering curve. Okay. Now they told us that the final data point 6 occurred immediately prior to failure. So if you want, this is the final point. This is the fracture point. Point 6 is the fracture point. We have that the yielding occurred at a load of 19.39 kilonewton. So the yield is somewhere between points 1 and 2. So yield is in between here. This is the yield point. We have that the maximum load is 29.42 kilonewton. So it should be somewhere here. So here is the maximum, and then the value of force will start to decrease. So here we have maximum TS, the tensile strength, okay, maximum load. So if you want, from this information, we can identify the different phases of in my problem. I can say that point 1 belongs to which region?
Elastic region.
Elastic. So point 1 should belong to the elastic region. From 2 to 4, I have which region? I am before necking. So I have the strain hardening region. So this is the strain hardening zone. And after point 4, I have necking. Okay. So here I have necking zone, and at 6 I have the fracture. Okay, so this analysis will help me after to know how to, for example, to find the strain hardening coefficients, etc. So first, the first question is to plot the engineering stress strain curve. So of course, whenever they ask for this, I should go back to the formula. I know that engineering strain is delta L over L. So I will just, to find the engineering strain, all I have to do is to divide the displacement here. I divide all these values by N. And of course, since the values of L are the displacement, the values are given in millimeter, so I divide by the value of L in millimeter, which is 100. From here, I get epsilon for the different points. And concerning the engineering stress, by definition, the engineering stress is the force applied over the cross-sectional area A. So I already the value of the force is already given, and I should pay attention for units. Since the force is in kilonewton, and the area, if I divide by the cross-sectional area in millimeters square, what will be my unit? So if F, I keep F in kilonewton, and I divide by millimeters square, I will get my stress in what? What is the unit? Gigapascal. Okay, gigapascal. Because Newton per meter square is Pascal. Newton per millimeter square is 10 to the power 6 Pascal, which is megapascal. And kilonewton per millimeter square is 10 to the power 3 times 10 to the power 6 Newton, which is 10 to the Pascal, sorry, which is 10 to the power 9. So it is gigapascal. Okay, so pay attention for units. After I find all values for all points, I can also add to these points the point 0, 0, okay, because I know that for a force of 0, the displacement is 0. So I can add this point to my curve and I can draw it. So let us see how they did it. So first, I represent the values in a table, and the units here will be in gigapascal since my force is in kilonewton and my area is in millimeters square. When I draw my curve, I get sigma engineering, function of epsilon engineering. And as you can see here, the profile, in this profile, it's not very clear where is the maximum. I have nearly here a flat plate. So if I want graphically to find the start of necking, it's difficult to see it here. This is why the true curve is of high importance. Okay. In this problem, because they gave me the maximum load, I can calculate sigma engineering maximum. But just from the curve, it's not clear where is my maximum. Okay. So I need many more points if I want to trap the maximum accurately. Now, the next question is to find the yield strength. So here they gave us, as the previous problem, they gave us the load for which yield will take place. This yield will take place at 19.39 kilonewton. So all I have to do to find the yield strength is to divide the yielding load by A0. Okay, and if I keep the force in kilonewton and A0 in millimeters square, I will get my yield in gigapascal. Then in part C, I want to calculate the modulus of elasticity. Here, I have several choices for the modulus of elasticity. First, I can do the same methodology of the previous problem because they gave me the yield at 0.2% of set value. But also, I have another option because I have 1 point before yield, 0.1. Okay, 0.1 is in the elastic zone. And since I know coordinates of 0.1, and I know that my curve starts from 0, 0. So I can also say simply that E is equal to what? E is equal to sigma at 0.1. Of course, engineering, sigma engineering at 0.1 over epsilon engineering at 0.1. So this is an easier way to directly get the modulus of elasticity. You can try to verify also by using the offset method. You will find a very close value for it. So we have two methods here to calculate the elasticity modulus. And the unit of E will be like sigma. So if sigma is in gigapascal, E will be in gigapascal. If sigma is in megapascal, the elasticity modulus will be in megapascal. Then they ask us to find the tensile strength. So to calculate the tensile strength, also as we did in the previous problem, we have the maximum load. We divide the maximum load by the cross-sectional area at the initial state A0. We get the tensile strength. And finally, for the percent elongation, always for the percent elongation, we consider the displacement at fracture. So we have delta L at fracture is 35.1. We divide it by L0, so over 100. We get that the percentage elongation is 35.1%. So here we will see in summary how we do the calculation for the different questions. So first, in part B, to calculate the yield strength, we divide the force, the load of yield over A0. And since we have here, they converted the force to Newton. This is why they got the yield strength in megapascal, because a Newton over millimeter square will give megapascal as unit. Now, for the modulus of elasticity, as I said, they considered one point in the elastic region, which is 0.1. So we can simply divide sigma 1 by epsilon 1. We get the value of the modulus of elasticity. And here, you get, since they used the value in megapascal, they get 59.3 times 10 to the power 3 megapascal. And if you remove times 10 to the power 3, you put gigapascal. Okay? Now, concerning the tensile strengths, we divide the maximum load by A0. And here also they converted the maximum load to Newton. So when dividing by millimeter square, you get your value in megapascal. And finally, for the percent elongation, it's delta L final over L. It's 35.1 over 100. So we get 35.1%. Now, next question is to find the strength coefficient and the strain hardening exponent in the flow curve equation. So as we said before, when we did the analysis, we said that these 3 points are in the strain hardening zone. So pay attention always when they ask you to find the coefficients, the strength coefficient and the strain hardening exponent. You should take points between elastic zone and necking zone. So try as much as possible to take points that you are sure that they are far from elastic and fracture and necking part. Okay, so here these 3 points belongs to the strain hardening zone. So you have the possibility to take any combination you want. You can take 2 with 3, you can take 3 with 4, and you can take 2 with 4. Okay, so you have 3 possibilities here. What we did here to reduce the error, we will calculate 3 values of k and n and take the average. In the exam, if they don't specify, they just ask you find this coefficient, to just take 2 points. Okay, but you should make sure to take these 2 points far from the elastic and necking zones to have accurate results. So here, 0.234. In the tables, we are considering that the first point is 0.0, so 0.00. Okay. Now, when we count points, if you count from here 1, 2, 3, 4, 5, then the number here will be, instead of 2, 3, 4, it will be 3, 4, 5. This is why here in the table here, when they did different calculation for the value of k and n, okay, they said we take points 3 and 4, and they mean here points 3 and 4, they mean by this 2 and 3. Okay, and by 3 and 5, they mean 2 and 4, and by 4 and 5, they mean 3 and 4. Okay, so we will take several combinations of points and calculate for each combination of points, calculate the value of n and k, and you will see that we'll obtain very close results. And the error is very small because all these points belong to the strain hardening zone. So how to do the calculation for any 2 points? What is the method? Of course, you should pay attention that epsilon and sigma are the true values of stress and strain, not the engineering values. Okay, so whenever you want to calculate sigma, k, and n, you will need to relate, because the flow curve is what? Is sigma is equal to k times epsilon true to the power n. Okay, and the flow curve will be coincident with, it will be in match with the true stress strain curve. So in order to find the points belonging to the flow curve, they should be, we should find epsilon true and sigma true of these points. So as we said, the 3 points of interest are points 2, 3, and 4. So I can calculate the value of epsilon true and sigma true for these points by simply using the relation between engineering and true values, because we have already calculated in a table what are the engineering values for the different points. So now you will use the following relations which we demonstrated in the previous problem. Sigma true equals to sigma engineering times 1 plus epsilon engineering, and epsilon true equals to ln times 1 plus epsilon engineering, to get the true values of epsilon and sigma. And once we are done with this step, now we are free to take any combination of points. So for example, if I choose to take 3 and 4, what will be the system that I will write? The coordinates of points 3 and 4 should satisfy the flow curve equation, which is sigma equal to k times epsilon to the power n. So the first equation I can write for point 3, I say, what is sigma true of point 3? It's 0.201626. This should be equal to k times epsilon true, which is 0.099845 to the power n. And I do the same, so I will obtain a first equation including two unknowns, k and n. Now I will write the second equation. So I will take point 4. For point 4, what is sigma true? It's 0.235135 equals to k times the value of epsilon true at point 4 is 0.198851 to the power n. This is equation number 2. Now, if I just divide 2 by 1, so equation 2 over equation 1 will give me 0.235135 over 0.201626 equals to k over k will simplify. I will get 0.198851 over 0.099845 to the power n. So in this equation, the only unknown is what? The only unknown is n. I can calculate the value of n. And once I get n, I can replace back or in equation 1 or in equation 2 to get the value of k. And the unit of k will be the same unit of sigma. So if sigma is in gigapascal, then you get k in gigapascal. If the value you used for sigma are in megapascal, then you get k in megapascal. You can repeat this calculation for point 2 and 3, and for point 2 and 4, and solve for several times for k and n, and you will see that you will obtain very close results. So here is the summary of calculation. So if you take points 2 and 3, you will get for n 0.223045 and for k 0.337086. If you repeat the calculation for other points, you can see that the first 3 numbers after the comma are nearly the same. So this is why it's very accurate, and you can take any of the points and you will get good results. Now, once we have the values of n and k, we will be able to draw the flow curve, which we will do in next system. Okay. Now, in question G. Yes.
No, the equation it's applied after yield or before necking.
Exactly. Yes.
But why didn't we take number 5?
Because number 5 is after necking. No, I told you here the numbering they are using is different than from the table. I will repeat it again. Look, here they are counting from 0. If you count from 1, so this is point 1, this is 2, okay? This is 3, this is 4, and this is 5. They mean by 5 here in the table, they mean 5 means 4, okay? Because they are counting from here. When they say 4, 5, it means 3, 4. They are not including this point in the calculation. This point is after necking.
Yes, I'm asking, مش number 5 هي إنه before the tensile
No,
force.
after. No.
لا.
Look, why? لأنه when we did the analysis here at the beginning, okay, where was the maximum load? The maximum load is 29.42. يعني here you start to have a decrease. Okay, so the maximum is between 4 and 5. يعني necking will start before 5. Okay, this
okay.
is why 0.5 is not included in the strain hardening zone.
حتى لو إنه الفورس هو 27 which is less than ال 29 بس it's considered in the necking. أنا قلت إنه لأنه الفورس is less than
Okay, it's less
maximum
يعني it's in
load.
necking صح؟ If the force
No.
is less than the maximum مش يعني نحن بالnecking force؟
إنه الفورس بصير بقل بعدين
Yes,
يعني.
exactly. بعد الماكسيمم بوينت بس يبلش النكينج الفورس بقل. إذا قلل بس يبلش يقل الفورس يعني صرنا بالنكينج بارت. وبالنكينج بارت الفلو كيرف ما بيصير في separation بين الفلو كيرف والترو كيرف. Okay? يعني you cannot say that 0.5 is in the strain hardening zone. 0.5 is in the necking zone. هلا it is very close إذا بدك لأنه 27.4 is close to 29 يعني just يعني بعدنا ب start of necking ال 0.5 بعدنا مبلشين النكينج يعني.
Okay.
هلا إذا if you take 0.5 هيطلع لك error بس ما بتكون كثير كبيرة ال error because it's close. Okay, but to be more accurate you should take يعني it's of course you should take points in the strain hardening zone. So you have 3 points in the strain hardening zone. You can select any 2 of these 3 points. Okay.
Okay.
دكتور does the force هنا بيقللوها قصد من بعد الناكينج ولا
لا يعني ما هي شو الفكرة؟ أنت بتصير تحط بتزيد الفورس تتعمل elongation to increase the elongation. إذا عايزة فورس أقل يعني اوتوماتيكلي هي بتقل يعني انت بهمك تزيد الالونجيشن بتشوف شو هي الفورس needed to increase الالونجيشن بما انه صار بدك فورس اقل يعني ما بقى في لزوم تعلي الفورس you can continue
يعني
elongation with a smaller force
يعني هيدا the minimal force needed to continue elongation.
yes exactly.
Oh, okay, thanks.
Okay, so let us continue. So now what is the next step? The next step is to draw the true stress strain curve and to compare with the engineering curve. Okay, so in order to compare the true stress curve to the engineering curve, we should plot them on the same graph. But you know already that the engineering curve is plotted function of epsilon engineering, okay, while the true stress curve is plotted function of true strain. So if we want to present them on one graph, we should choose something in common between. يعني ولا epsilon true ولا epsilon engineering. What we can do, we can, for each point, what is common? It's the displacement in millimeter or the length of the specimen. يعني if you want to compare on the same graph, you can draw sigma engineering and sigma true function of L or function of delta L. لأنه what is delta L? It's L minus L0. So just it's a difference in a constant. So the difference is a constant. So here, this is what we will do now. We will draw both curves function of L or delta L and see in this way we can compare their values. I will open a new session to continue, okay?